Now, thank you all for being here. Maybe you recognize here the city of The Hague by night. That's where I live. And all these lights symbolize why we use energy for working, for being comfortably warm, cooking, cooling, showering, security, and so on. And you see the little blue spots, that's the power plant of The Hague. It's in service since 1906. And while producing electricity, the turbines also produce a lot of heat that is injected into the district heating of the city. And as such, that is a very sustainable solution because waste heat is reused, of course. But will this plant go for another 114 years? This is absolutely not sure, because it is extremely important and urgent to move to a sustainable energy infrastructure, meaning at one side, reducing the demand where possible, and at the other side, switching to renewables. There are people believing that when you use renewable, or when you have a circular system, there is no need for reducing the demand. I don't think you belong to these ones, but there are 4 reasons at least why that is not true. I will try to place the context of this lecture. On your left, you see the right things, the renewables, starting from below wind turbines and solar panels for electricity, biomass for cogeneration of electricity and heat, geothermy for solar heating. We will also need storage like batteries, hydrogen, storage in the ground, and so on. These technologies also use materials that must be produced, leading in turn to environmental problems, including space used to accommodate them. Although their impact on the environment is many times lower than the impact of fossil fuel use, it is still significant. This is the first reason why we should also be efficient and try to reduce the demand, like lowering the temperatures a bit. A second reason to be efficient is that if we don't, the energy demand will keep increasing simply because the number of people and the number of buildings increases. And a third reason is there have been evidence collected the past years that 10 to 30% of energy use in buildings is just wasted because of improper control and steering of the energy systems inside buildings. That's the first picture. In the Netherlands, 11% of our energy comes from renewables. That's not much, the lowest share of European Union, and that is completely offset by this 10 to 30% energy waste. And the fourth and last reason is that renewable heat, either heat pumps or aquifer thermal storage or geothermy, is always low temperature heat. Low temperature heat, to be comfortable, needs well-insulated buildings. That's the picture below. So my chair address only specific parts of this context. The ones being in relation with energy efficient buildings and the control of complex renewable energy equipment in buildings. And we do that by making use of data analytics, the subject of the lecture today. In this lecture, I will take you through the use of data analytics for different purposes. I will not focus on data analytics methods, but on the applications of this. So it's not a course on machine learning, let's say. We use, in fact, data analytics and large collections of data to design, monitor, and control energy and indoor climate systems on an efficient, sustainable, people-friendly, and smart way. And we do that at the level of buildings and the built environment. What will I tell in this lecture? I will first give a short explanation on data analytics, and then I will take you to the 4 themes we are working on at the moment, which are large-scale analysis of the building stock, people-friendly systems, digital building inspection, and self-diagnosing systems. But we first start with the data analytics. I hope you see this symbolizes a kind of data circulating through the built environment. But let's go to this. When it comes to data, many terms are used all together, and it is sometimes a bit confusing. So I try to order it a little bit for you. We have data science, which is a kind of a combination of data visualization, data mining, machine learning, deep learning, and we also have the artificial intelligence part, which is for a part based on machine learning and data mining, but also on more engineering things and rules. When I talk about data analytics, in fact, it's also a bit of mixed of all these things, depending on what we want to do. I still have home an impressive collection of Legos and heritage from the time my children were young. I want to explain very shortly what type of data analytics systems we have, and to stress the importance of models. We have a bunch of data. We can do data visualization with that. We can also do data mining. That's on the right part of the picture. And data mining, we could also call it unsupervised machine learning methods, like making clusters of things by just looking at the characteristics of some parameters. But even more interesting is to combine this with models. And in machine learning, in fact, we use a lot of models, and a regression model is already a model. That's what you see in the machine learning part. And we can go further by using deep learning, which is a kind of automated tryout of different types of models and finding which one would fit the best. And of course, as I said, the artificial intelligence part based on these techniques, but also on rules. When should I do what? And that can also be based on analysis of future trends to make decision on what you should do now, and on engineering and on modeling. Okay, that's the shortest course machine data analytics I have ever done. But let's look at the application. I think it's more interesting for now. In my chair, as I already said, we focus on two parts. The first one is the building level, which we could not say really that it is epidemiology. It's the study of all data coming from building energy management systems. And the second part on the right part is the analysis of data for the building stock. That's the real epidemiology, in analogy with health, of course. Okay, let's go on with the part about the large-scale analysis of the building stock. Why do we need analysis at building stock level? Now, we have 3 reasons for that. The first one is that we want to have impact on the large scale. The second reason is that we need policies to steer on the built environment and the energy transition, meaning that we need data at stock level rather than at building level. And the third reason is the context. We are used to reasoning and to make a scientific experiment at lab level, or at least at unit or individual level, in quite well controlled circumstances. For instance, we can study in lab very carefully and in much details what are the properties of a certain virus or winter wheel or lighting bulb. We can also go a step further and test them in a precisely defined context. How is this patient coping with the virus? How is the wheel behaving in a car driving on the snow? How are the lights used in this building below? But what happens at the large scale? When not the technique itself has most effect, but the context. How does the virus spread through the population? How does the car behave when it is hit by others in the snow? And maybe that in the typical house I studied, the people were not energy conscious at all, while most people are. What does that mean for the large scale? It may be for one household very important to lower the temperature by 2 degrees because their thermostat is at 25 degrees. But it doesn't mean anything for national savings if the vast majority of people's thermostat is at 18 or 19. And you can't ask them to lower even more. So that brings me to the question of how do we know what happens at a large scale? Up to a few years ago, there were very little data. Data was scarce. And the only way to develop thermodynamic models of buildings and the only way that we had to study the housing stock was to develop thermodynamic models of buildings and to validate them by making measurements at a small scale or at component level, like a wall. Because measurements were very expensive in terms of time and money, as they still are, by the way. When there was some confidence in the model, it was then used to predict the energy use of many different buildings at the large scale. Such a model entails, of course, a part about the weather, a part about the building geometry, a part about the energy systems, what we call the HVAC system, heating, ventilation, and air conditioning, and about the internal heat loads. And of course, to deal with the behavior of people, what we did in building simulation is to introduce schedules of use. And the simulations are then based on heat transfer equation, resulting on energy, temperatures, and comfort indications. From the 70s, a lot of research has been done on such models. See all books on the left. They are also used in practice by designers and policymakers, and we can have a lot of confidence in these models. So such models were used to analyze the building stock and to make prediction of energy usage when applying measures like insulation or using heat pumps instead of boilers. But for a few years now, there is data, thanks to CBS, for instance, in the Netherlands, our national statistics, that register yearly a lot of information on households and energy use at address level. And thanks to the European EPBD, the Energy Performance of Building Directives, by which some kind of registration of energy labels is mandatory. And also thanks to the Dutch platform of housing associations, in our case, who were registering on a detailed way construction characteristics of buildings, we have been able, with a series of PhD researchers, to compare and analyze the actual energy use to the modeled one on the large scale and at address level. We can learn a lot by just making visible what happens. And you see here what happens. This is a study on 1.4 million of social houses, from which we compared house by house the energy, the simulated energy use by the models used for the EPBD and the actual energy use. And you see huge differences. This is called the energy gap. We have classified for this picture the energy used by energy levels, going from A to G, A being the good level, G being the poor levels. And you see in gray the modeled gas consumption, and you see in white the actual gas consumption in a specific year, with correction, of course, for the climate year. And it is very visible that there is a strong overprediction of the energy use in the poor levels and a strong and a quite high under prediction of the energy use in the good labels. And that has strong consequences, because if you want to renovate a building from a label F to a label B, and you trust the simulation, then you think that you will go from a very high consumption to a very low one, saving 58% of energy, while in practice, what we see is the energy savings will be only 33%. So this has at least two very practical consequences. The first one being that the actual carbon emission savings is almost twice smaller than expected. And the second consequence is about the returns on investments and costs. Normally, the costs of renovation are paid back by lower energy costs. Unfortunately, the energy savings are lower than calculated. From the scientific point of view, a main question is, why is this happening? We thought that our models were right. Many people would directly point out to behavioral aspects like rebound and pre-bound effects, and indeed they are there. But it's not the only thing. I will come back to that. As already said, the models themselves are okay. The problems lie in the input to the models. First, indeed, we know very little about behaviors and use patterns that influence the energy use. We work with best guess about presence of people, thermostat settings, ventilation patterns, and we know almost nothing about feedback loops taking place between behavior and equipment and buildings. For instance, apparently, the temperature in well-insulated houses seems to be higher than in non-insulated houses. Is this energy wasting behavior? Maybe, but we have more and more evidence that it is also simply that the house do not cool down anymore. Next to the behavioral inputs to the models, there is also the input of building characteristics themselves and the input of the energy systems. I already told that we use data at building level coming either from archetypes or from building inspections. But building inspections are very costly and time-consuming. In fact, it is not to be done on the large scale. Or maybe it can be done, but it costs a lot of money. That's why the input is generally based on these archetypes per construction year, per ventilation systems. The hot tap water, for instance, is generally modeled on a very simple way, depending on the floor area and sometimes on the number of, or on the size of the household. What we hope is that data and machine learning can help us to find out the right input parameters to the model. So instead of feeding the machine learning algorithms via a simple equation as on the left side in blue, okay, sorry, there is, yeah, sorry. We feed them with the complete building model to find out what should be the right standard value concerning building properties, energy systems, and behavior in each of the archetypes. That is what we call calibration, and we are not the only one doing it. At the University of Ghent, you are doing that also a lot. I've seen many people in the public that are also working on this subject. And in fact, by disaggregating the data, we can somehow find building properties, energy systems properties, and occupancy behavior. And after this calibration, the models can predict much better. I have here an example of the thesis of Paula van den Broom. You see the performance gap before the calibration, and you see it after calibration, and you see that we can estimate much better the output of the models this way. It is not that easy to do, and there is a lot of research needed to do that, and there is a lot of ongoing at the moment. Mainly on which type of machine learning algorithms are best suited to which types of model. Maybe we can also use unsupervised methods to define better buildings archetypes, to define better occupant archetypes, to define the efficiency of energy systems, and to study the efficiency of renovation measures by using cross-section longitudinal data. Another area of research in this relates to the granularity of the data needed. This is important for privacy issues. Yearly data is sometimes enough. There is no need for 15-minute data. So it is very important when we are looking at the complete stock. We don't need this 5-minute data, at least not for everything. So it is important for the transition to sustainable heat, which will certainly include smart district heating grids. For these grids, knowing a current and future energy performance of buildings at the level of cities and neighborhoods, that's quite essential. And maybe we don't need to know this at address level, and is some kind of aggregations like at postal code level is enough. And of course, urban models obtained with a GIS model like CityGML will be of use, and we have to look how to combine them to our energy models. So looking at the large scale was quite an eye-opener, but to understand better what happens, we still need more detailed study at individual house level. In the next chapter, I will highlight research on the 3 levels of input needed by models: the building, the energy system, and the behavior. So let's start with the behavior. And take it broader towards what I would call people-friendly systems, because in the end, that is what does matter. The people, their comfort, their health, their safety. It's not only about energy, or energy is in fact about this. I already told it, we are in need of some kind of categorization, not only as input for models, but also as a mean to understand energy behavior and as a mean for finding solutions that work for large groups in order to make impact. You see on the left side 5 clusters of behavioral patterns fully determined with unsupervised data mining methods in the thesis of Olivia Gerasantin a few years ago. One of these groups is the conscious warm, left below, in which people appear to be significantly more often than others, more often home, to be older, to have lower incomes, and appreciate having a warm house. Obviously, also, if we were not able to find a correlation between these groups and energy use, it says something about what sustainable technologies to offer. This group could benefit from balanced ventilation systems, for instance, rather than from CO2-controlled ventilation. Recently, in the group of colleague Bluysen at TU Delft, they came with much more refined clusters, also taking into account the habits of people, their emotions, and their feeling of control. Study on patterns of thermostat settings were also done. That's the right picture. And here too, patterns of use can be determined. And that brings me to thermal comfort, very important for the acceptance of new technologies. And of course, I needed to have cats somewhere in this presentation. You know, when we use traditional system like a gas boiler, the temperature of the radiator may be very high, between 70 and 90 degrees. We are used to that. That's very comfortable. When we go to more modern technologies like condensing boiler or high temperature geothermy, the temperature goes below 70. And when we are talking about heat pumps and a low temperature geothermy, the temperature of the heat is lower than 50 degrees. And that may be perfect if the house is well insulated, if you are not, if you do not feel the cold from non-insulated walls. So that ask for a minimum level of insulation if we want to avoid people feeling like the cat on the ride. In our field of research and engineering, different theories of thermal comfort have been developed in the 70s. Probably you all know about them, based on the measurements in climate chamber. We can question the validity of these theories when used in the real world context. It's not possible to collect data more, it is possible to collect data more easily. For instance, we used an app that you can see on the left to study how people feel and to couple this data with other data measured indoors, like temperature or humidity. In the picture, you see on the horizontal axis what the feeling should be according to the theory. Feeling neutral is 0, below 0 is feeling cold. The vertical axis is the thermal sensation as reported by the occupant. If the measured sensation would be in accordance with the theory, all points should be on the diagonal. Although the sample size does not allow in this case for any generalization, it seems that people feel comfortable while we predict they should feel cold. One axe of research in this is that people seem to be just satisfied by what they have and get used to it. If the house is 18 degrees and does not come high, the temperature does not come higher, then they get used to it, put a sweater and are happy. If the temperature is 25 and does not come lower, people are in t-shirt all winter and are happy too. That should mean something for energy efficient systems. To conclude this part, it is evident that research is needed on the relationships between energy behavior and actual energy use. A question also is if households characteristics like the number of persons, the age, the fact of working home or not is not overwhelming the energy behavior. And another question is real world comfort is the same as climate chamber comfort and how to measure it. It's burdening for people to, if we want to do these measurements. We try to do it, but still it's not completely easy. And a last point, very important, is to study if we further can design systems and interfaces that fit to people's needs and help with energy efficiency and a healthy indoor climate. I think in the end, we should have systems that adapt to people rather than asking people to adapt to systems all the time. We are now coming to the fourth part of this lecture. Let's focus on the building itself and on the possibilities for digital building inspection. We have seen earlier in this presentation that making physical inspections is expensive and therefore not done. In the future, there will be more and more smart meters. Can we maybe use this data? Data mining and visualizing what happens is already a big step. Let's start with the right picture, data coming from the smart meter. If we order this data according to the outdoor temperature, the two pictures below, we can discover patterns of use. In the building left, there is a clear relationship between heating consumption and outdoor temperature, and even a week and a weekend pattern. In the second one, on the right, the relationship is much weaker. Probably the building is well insulated and warm tap water is the biggest consumer. In fact, by making simple multivariate regression analysis, it is very well possible to predict the energy use with a few simple variables like time of the day, outdoor temperature, solar radiation, and wind velocity. This type of energy analytics software is already used a lot to buy and sell energy on the energy markets, and also start now to being more used in building energy management systems. However, these regression models, they cannot be used to make buildings more energy efficient. They are not presenting the right buttons to push on. I cannot change the solar radiation or the outdoor temperature. So we need other models. For instance, by combining presence and CO2 sensors, the two graphics left above, right above, we could determine if too much heat is used during absence or if the ventilation should be put higher. I will now go a bit further into the subject of determining what types of models are suitable to advise people on renovation measures. Do you remember that we talked about large-scale discrepancies between modeled and actual energy use? Yeah, I'm sure you do. On the right side, such a diagram showing the average difference in more than 2,000 houses this time between the expected and real saving when insulating the house. So that's the only thing what has happened in the house. We insulate, the walls were insulated and only the walls. And the actual energy use, the actual energy savings were measured. So the energy was measured before and after the renovation on a complete year, and the same for and modeled as well. And you see here too, for such a simple measure, you see here two big discrepancies between the savings. This big discrepancy, you also may remember that we said that this could come from a poor estimation of the building characteristics, in this case, the heat resistance of the wall, the R value. Look carefully at the wall on the right. It has little insulation, but in a few seconds it will be strongly insulated, I guess. Yes, you will see this, measuring the wall insulation in a lab is not complicated at all. The steady state heat transfer in the wall is described by very simple equations based on the thermal resistance, the temperature difference between both sides, and the surface area. That's the model above. You calculate the energy with the first resistance, with the second, and the difference is the energy you will save by insulating the wall. That's very simple. But these are pictures now of the real world. I'm not talking about new buildings of which the construction is known and documented. I'm talking about the other 90% of the building stock where that is not the case. Because the real world is not steady state, temperature and fluctuations all time, and there is solar radiation coming on the wall. In situ measurements cost weeks. They are therefore not done, no measurements. We have worked on a new and quicker method to make in situ measurements, but still it costs time, it costs money. You could also do it another way by boring a hole in the wall to look at the construction, but people are generally not amused. So it would be really beautiful if we were able to determine this heat resistance just by looking at the smart meter data and maybe adding some additional informations like temperatures on the walls. That's unfortunately just looking at the smart meter data, as I just said, is not enough. And it is not only about the data, it is also about the models. Which models fit with the data and which machine learning algorithms will fit with both? That's the problem. Our first model, numbered 1 on the right of the slide, is the one used in lab. But the Q, the heat we are measuring with our smart meter data, is not the Q that goes through the wall. Another problem is that with our home automation systems, we are not measuring temperatures on the wall, but air temperatures. And because of the varying outdoor air temperature, the model is now transient, not steady state, and heat accumulation in walls becomes important. So model 2 may be better, the model on the left. But still, the heat measured with the smart meter is not only a result of heat losses through walls, but also from ventilation and solar radiation and internal heat gains. So we need a more complex model. Model 3 would fit reality much better. Unfortunately, because of the math, this model 3 have multiple solutions, and I will never be able, whatever the machine learning algorithm I use, to say which of the solutions to attribute to R or to RV. Imagine Q is 6. Yeah, 2 times 3 is 6, but 3 times 2 is 6 too. So only if we introduce additional information in the models, therefore, if we extend the model, like adding a dependence of the ventilation on wind velocity, we could be able to discriminate between both. Another solution is to add additional temperature measurements, like in model 4. Navigating between 2 simple models and 2 little buttons to push on and 2 complex models with too many buttons, we cannot even measure. That is an art. To conclude this part, I would say that there is a lot of research needed on the extracting of relevant information in practice, like the R value or the infiltration flow rates. There are a lot of efforts still needed to predict the effect of measures like insulating, ventilating, heating, habits, use of techniques, and the more when you predict the effect of combining these measures. There is also a need of evidence-based design for better products. To do that, we really need not only data, but models. So we need at one side the math with models, we need the data with algorithms, and we need system knowledge. And system knowledge, that is knowledge about the building, about the energy systems, and about the occupants. With all these 3 parts, or in fact 6 parts, we should be able to go further. So data analytics is not only about just data and machine learning. That's too limited. Now I come to the last chapter of the lecture, which you see here a robot. It's to symbolize some kind of artificial intelligence that we could implement in our buildings' energy systems. We saw at the start of the lecture that the quantity of energy that is wasted in building is at least as big as the quantity of renewable energy produced in the Netherlands. It would be so wonderful if we were able to design systems in which self-diagnosis is embedded and even self-optimization. This becomes even more important because renewable-based energy systems in buildings are complex from nature. Let's take the example of the building of the Hague University of Applied Sciences on our campus. It is exemplary for the many buildings in the Netherlands with aquifer thermal storage, with one advantage more than being exemplary. It has a very extensive building management system storing for more than 10 years now millions of data points. So to make analysis, it's really nice. Starting on the left, you see below the aquifer thermal energy storage, you see that this ATES system is connected to a heat pump, or you see that better on the right picture, and to a boiler, so to a peak boiler. You see that there is also a dry air heat exchanger in order to replenish the warm well of the aquifer of the ATES systems when needed. You see that the building is also equipped with a giant solar heat collector on the roof and PV cell, and the solar heat collector is also used to load the warm well with heat in the summer when there is an imbalance. And by the way, the air heat exchanger on the roof is used sometimes for cooling the building, but also sometimes to load the cold wells in winter in case the imbalance is different, the other way wrong. So those are complex systems, so complex controls. And we are going to look at them. On the right, you see the data stream being produced. On the left, you see a process and instrumentation diagram of the energy and indoor climate system, a principal scheme. Each HVAC system worthy of the name in the world has such a process diagram. It is produced by the engineers designing the system in order to know what to couple with what and how to operate it. It describes all flows of water and air coming in and out of each component and subsystem. It describes all measurement points and all controls. This is, in fact, a big model. With this, it is very simple to write energy balances and mass balances and pressure balances. In short, such a process diagram is nothing else than a model, a bit more complex than the one on the left, but okay. There have been a lot of work done by many researchers and companies on analyzing the historical performances of parts of such an HVAC system. Imagine that data science researchers would be looking at this data of the condenser of the heat pump. They would probably be very, just look now at the black points, not the other parts. They would be very happy to discover that apparently this condenser has two working modes, one in winter at low temperatures, one in summer at high temperatures. Maybe they would express doubts about the quality of what happens in winter because the cloud of points is very large. But what would an HVAC expert do or say? He would have expected this winter and summer working modes because that is how the system was designed. And he would also know what the control set points are, the red line. So he would immediately say, oh, winter is okay, summer is not, the condenser temperature is much too high. That's why the COP of my heat pump, who works as a cooling machine in summer, is too low. Problem kind of solved. So what we asked ourselves is it possible to mimic the way the expert is thinking? I know expert systems have a very bad name because the quantity of work to set them up is giant and they cannot cope easily with changes. But that was in times of data scarcity. Data have changed everything, and expert systems of now, they are just called artificial intelligence. So, to make a diagnosis, we can look for inspiration in health sciences, how a doctor makes a diagnostic. Of course, we can look at trends, but we can also go further. You see here, a doctor makes a list of symptoms, like do you have a sore throat, are you sneezing, do you have a loss of appetite, and based on that, he finds the disease and then he finds a cure. We apply the same thought. First, we make a list of all possible symptoms. A symptom is everything that can be observed on an automated way and therefore relates strongly to the sensor data. During operation, all data coming from these sensors is observed automatically and compared with the specifications. If it is not in accordance with the specification, there is a symptom. And checking regularly which symptoms are detected during operation leads to finding the causes of these symptoms, the disease of the system. Here too, that's the right part of the graphic, we need to do once an inventory of all possible faults. This can be done at the same time as the process diagram is set up by the engineer. Basically, all components, sensors, controls, and models present can be faulty. It is a once-in-a-time inventory. And then you have to couple the symptoms to diseases. This also is a once-in-a-time work resulting in a diagnose engine. During operation, the engine will then identify faults automatically based on the data it receives. And the diagnose engine is based, in our case, on Bayesian statistics. That's not the only way to do it, but that's what we tried out. That's what we tried out. And that is the Bayesian statistics is the probability of events occurring, in fact. So from the PID diagram on the left, an engineer can set up symptoms and fault lists and set up basic relationships between these faults and symptoms. That's the diagram in the middle. Basically, he can read them from the process diagram. Then he could pick up in a library the right Bayesian models, which will, during operation, deliver the probability of certain components or controls being faulty. Just like in the diagram below, where measurements during 28 days shows that sensor TT044, the blue one, is with almost 100% chance faulty. Most important, by applying the diagnose system on the HHS building, we showed that 25% of energy could be saved. And this, while the system is one with the reputation of being one of the best functioning one in the Netherlands. So that is a research that we expect to continue with the Brain for Building projects that we just acquired in the Netherlands. So my hope is that within 10 years we can have really self-diagnosing building energy systems, that we will have solved time granularity issues, and then that next we are making tryouts on historical data, but that it will also be able to work real time, that there will be standard libraries and effective combinations of data mining, machine learning, and system approach. So to conclude, that's my last slide. We have seen that in energy analytics, we use large collections of data to design and monitor and control energy, that there is a lot of research on that. And that we can also use that to try to design better and more people-friendly systems, that we can do that at the level of buildings and the built environment, and that for this we need not only data, but also models and system knowledge. Thank you for your attention. I think I have been a bit too long, but...
It's perfect. Thank you. Thank you. For your interesting presentation. We now have time for questions, so I invite every one of you, if you have questions for Professor Itard, to post them in the chat, and then we can ask a selection of them. I already have a more provocative question, I think. So you showed some results of an analysis between the modeled thermal comfort and the experienced thermal comfort.
Yeah.
Based on this comfort study, it is shown that in reality people accept lower set point temperatures, which according to typical comfort theory would be too low. Yeah? So the question is, do we need to lower then set point temperatures in schools and office buildings to train people to adapt to colder environments? And
yes,
a solution for saving energy in the building stock?
Yeah, I think that's a very good question that we are asking ourselves as well. Should we do that? I don't know, but I would like very much to get more experience with that. And I think it would be a good idea to at least try if we can use lower thermostat. Maybe that a smart thermostat can lower slightly the temperatures while you think it is not, and then we could observe what happens. I don't know if we can solve that problem, because apparently the more we go in time, the more people like high temperatures, or that is also maybe because we sell them higher temperatures, or because it is nice to wear less clothing. But I think this is a real question. And in fact, if I look at my own practice, I think we can indeed try to train ourselves to use lower temperature. And I know that there are also very interesting studies at the University of Maastricht by Professor Lichtenberg about the physiological aspects of health, and that health is not the same as comfort, and that what we need for health is not necessarily comfortable. And that, for instance, having in a building big variations of temperature is not comfortable, but it's better for health. So I think this kind of things are really very interesting to study further.
Yeah. In that study, by the way, were those PMV values corrected for clothing? Because it seems
yes. They were corrected for all parameters. Yeah, yeah. But of course, it's it depends on what people. The quality of the result depends on the quality of the input, of course. And people had a kind of app where they could fill in what their clothing was, in such a way that we could make an evaluation of the clo values.
Yeah. Okay.
But it's quite labor intensive for people to fill this app many times.
Yeah. I have another question here related to the renovation challenge, which is part of the European Green Deal. So the question is, there are very promising foresights in the data-driven approach for buildings, but there is a big renovation challenge for the existing building stock, whereby no sensors are present in the majority of buildings. Where best to start in setting up data collection? Which sensors first to install in existing buildings, in addition to a smart meter, in order to have most efficiency gains? What is your opinion?
Yes, yeah. Now, of course, smart meters are kind of necessity, maybe to give people feedback on their energy use, and maybe to help them by benchmarking with what other people are doing, because benchmarking apparently is something that is very powerful in helping people. Although there also are many studies showing that that benchmarking works for a few weeks or months, and then people stop looking at it. But if we want to go further, I'm quite sure we need at least temperature sensors in each rooms in order to control the heating in the rooms on different ways. Maybe that would be a good way to save energy. And I know that is in the Netherlands, there is only one thermostat, but I know, for instance, in Denmark, although it's much more usual to have a room thermostat.
Yeah, and the thermostat data are typically not logged or collected.
Sorry?
The thermostat data are often not available. So that
no, it is also a problem. So you need a smart thermostat by which you can collect the thermostat data as well, and that is what we can do in research projects with the industry, but that is not mainstream. It is not done everywhere, and of course we have to take care of privacy problems. So it's a big question if we should measure everywhere or only in samples large enough to say something scientific.
Yeah, you mentioned privacy problems. It's also raised in one of the questions. What about smart room controls for collecting heating data, and what about GDPR?
Yes, yeah. My opinion is, you know, when we do research, it's a research situation. So we organize it. We ask for permission of people to use the data. It's quite cumbersome to do, but we do it. Collecting the data on the large scale is another problem. In the Netherlands, in principle, the energy companies are not allowed to give the data, only aggregated data per each 3 months to research institute. So if we want to collect them, we need to collect 10 minutes data, for instance, or 5 seconds data. We need people to agree with that. So it's a lot of work in the pre-phase, let's say.
Yeah, so that would make it a problem to use those data to define priorities in renovation, for instance,
Yeah.
to define which houses should be.
Yeah, I think we have to, maybe we have to make a difference between what we need to make research and to produce results that will help for the renovation, and then later, and what we need to make sure that the houses in their operational work are quite optimum. And I think you don't need, if you want to make an optimum control system for heat pumps in houses, you can have a good control system. So using a lot of data, but that remains into the house. So maybe we need to have different levels of communication. We need some aggregated data to communicate with the outdoor interface, like a microgrid outside of the building, and we need a building energy management systems that do not need to communicate with outdoor, I think. And we, of course, we need everything for research purposes, but we should separate it, I think, from the point of view.
Yeah, the question here is I guess, more related to how to upscale it and use these data for policy. And for instance.
Okay, which data would be needed to upscale for policies?
Yeah.
Yeah.
For instance, in defining the priorities in renovating the building stock, now we typically use EPC rating results, which we know are have a low reliability. So the question could be if it's not better to use the actual measured energy data to define targets and to define priorities.
Yes, sure. But if we do that, yeah, that would be very good. But if we do that, then we need to correct for behavior and for household size. So it's never completely right. If we use model, we don't capture the behavior. But if we use actual energy use, we do capture the behavior, but much less the building itself. And we shouldn't punish, for instance, households with 5 people in comparison with households with 1 people. So it's a bit in the combination of all these things.
Yeah, that's why we also need.
We need much better occupancy characteristics and archetypes.
Yeah. And that's why we also need more data on indoor environmental parameters. One of the participants also mentions carbon dioxide sensors, for instance, in combination with smart.
Yeah, indeed. And because also we think that it's not all about energy, it's also about the quality of the indoor. That's why we need energy systems. And CO2 is not even measuring the quality of the indoor, it's only a part of the quality of the indoor environment. But still, it's already something. And it also helps characterizing the ventilation system. So it is an important thing. And we still see, I don't know how the situation is in Belgium, but we see many houses in which the CO2 is really very high, so indicating very poor ventilation.
Mm-hmm. Yeah, that's what we also experience now with
yeah.
pandemic, that there's a lack of sufficient ventilation in many
yeah. In older dwellings and in new dwellings, we see it in both. Yeah.
Mm-hmm. Okay, we have the habit to try to close down the lecture after 1 hour, so we have been in this lecture for more than an hour now, so I don't see any urgent questions anymore. Oh, wait, there's still one. Let's see. So let's take this as the last question. I experienced myself that 20 years ago I was satisfied with 20 degrees C room temperature. Now, 20 years later, I need 21 to 22 degrees to feel comfortable. How can this human physical evolution been taken into account in your simulations? This is the question. Can you comment on this evolution? And
in my view, it is an evolution that is coming from additional money that we have to buy additional comfort. And we could make predictions about how the temperature will keep, the preferred temperature will keep increasing, and introduce that in simulations. Or we can try to not do that and to reverse this trend.
Okay.
Yeah.
With that, I propose to close the 15 minutes of questions, and then I can only invite you to the third lecture in this series. This third lecture is scheduled on the 29th of April, also at 7:30 in the evening, and the speaker is Janet Reyna. In April. She's from the National Renewable Energy Laboratory of the United States. So you're also very welcome to point this out in your agenda. You will receive an invitation through the same way as you were announced about this lecture. So thanks for attending, and I wish you all a pleasant evening.
Thank you very much. Bye-bye.
Bye.
Thank you for listening and the discussion.